Welcome back, ladies and gentlemen. We're going to be continuing with aromatic hydrocarbons. The last video was pretty short. This one, not as short, but it shouldn't be as long as the isomer video. All right, so as we can see here, right, we've got some coffee grounds here. We've got a nice cup of coffee, and the aroma, the odors of the coffee are mingling around. Some people like the smell of coffee, some people don't, but you probably like the smell of something. And anything you like involves aromatic hydrocarbons. Aromatic, of course, in this case means aroma. So what's going on? Well, we've studied straight chains with or without branches. We call these aliphatic. Sort of a fancy way to say it's fat. Most widely studied organic compounds are actually rings, which we call aromatic because they often have an odor. Sometimes pleasant, sometimes not so pleasant, but they have an odor. They are something that our nose is capable of detecting. It is somewhat rare for us to run into a series of compounds that we can detect with our nose. Our nose is, it's good, but it's no dog nose, right? We're all about the visual sight more than the olfactory senses. There's the fancy word for you. Our sense of smell, not great. So the most common aromatic is something called benzene, which has an incredibly unique structure. And we're going to look at benzene here because it's kind of key to understanding a lot of what's going on here. So benzene is very similar to cyclohexane. We mentioned cyclohexane way at the start of this, and we mentioned that it was a bunch of hexane in a ring structure, okay? So here's cyclohexane. Right, as mentioned, we've got it in hexane, which means it's got all saturated, right? All the single bonds it can hold. Here's benzene. Think we can immediately see what the difference is. Not saturated. So, in some ways, this is a hexane, this is a hexene. In some ways, we never call it hexene. We call it benzene. And, ene. Ah, there it is. So the reason the ben part at the front, history, right? Of course, obviously we came up with these things before we fully came up with the naming system. We kept the old name because it was historic and very important and useful, and old people didn't want to change their mind. It's called benzene, okay? I'm sorry. It's got an ene ending at least. So these double bonds are not the same as normal double bonds. They're different in a very unique and special way. So the problem is that the bonds are the wrong size. So the bonds of benzene are 1.4 angstroms. So it's like a unit of measurement, right? You got like 1.4 meters, we could pretend, right? So a meter would be about from where my fingertips are to this shoulder, so that's a meter. So 1.4 might be to about maybe my elbow or so. So it's like about, the length of the screen here, give or take. But this is a problem because a single bond is 1.5 angstroms, which means that benzene's bonds are too short compared to just any old chain or aliphatic hydrocarbon. Okay, they're too short for a single bond. That's fine. They're too long for a double bond. A double bond is 1.34. Now, the difference there is pretty subtle, like we're 0.06 different. But it is still different. And it's noticeable enough that there are some unusual properties and behaviors of benzene. Chief among them, we can smell it. Now, that probably seems very arbitrary, very picky. But that's how important benzene and its various compounds are, that we have studied it to that level of detail. Do I expect you to memorize these bond lengths? No, I don't. I wanted to use this as an example to explain this, right? Now, why would double bonds be shorter than single bonds, and why would benzene be in between those two? Okay, well, benzene's in between these two because it sort of behaves like halfway between these two. It doesn't have a single bond, it doesn't have a double bond, it has like a 1.5 bond, which is weird and encourages many of its unique properties. But why would double bonds be shorter? Well, think about it, right? If you've got one hold onto somebody, you can sort of be pretty far away. But if you're two holds, well, you immediately I immediately had to rotate to be a little closer. I had to be pulled in a little bit more. And that's normally the case. A double bond pulls a little tighter, pulls the atoms together a little bit more compared to a single bond. So this led chemists to conclude that the aromatic ring is sharing electrons in a unique way. This is critical. This is called a hybrid structure, and we draw it like this. To be fair, we also draw it like that. Right? This is a hybrid structure over here as well. But generally, you're going to see it with this circular shape. Now, let's break it down. I said it's like a 1.5 because it's sort of like in the middle here. What's sort of happening is that the electrons in the ring are being shared across the entire ring all at once. It's like they get to move around on the highway. They can explore anywhere they want in that 6-member ring. And this gives benzene some very unique properties in how it behaves. I've said that like 4 times. What unique properties, Mr. C? Let's find out. Benzene is an excellent non-polar solvent and a great starting material for dyes, explosives, medicine, and cancer. That last one is a little unusual. I mean, explosives were already pretty unusual. Let's take a look at some of these. Toluene, that's a solvent. Naphthalene, that's, what do you call it? Mothballs. Right, that mothball smell. If you've got some moths, you want to keep them away from your clothes because your clothes are made of cloth and the moths will eat them. Naphthalene will do that. Mothballs is right there as well. Right, so then we've got those. Photographic developer. We talked about this in some length here. We talked about the nature of how photographs used to be made, and you'd have a photographic plate and how the plate would be inserted into, would have a chemical treatment on it, and when light would hit it, it would chemically react. But then you'd have to cover it up to hide it from light in order to freeze the level of chemical reaction. That would give you your photograph. But you wanted to develop that film. You wanted to make it so that way the reaction would just stop entirely and never continue. So what you would do is you would dip it into a series of chemicals. This is one of them. Next one, we got aspirin. That's medicine. Good one right there. Trinitrotoluene, that's dynamite. That's explosives. Right? The way that this stuff would work is actually pretty straightforward. You take your TNT, trinitrotoluene, by itself, very explosive. Nitroglycerin, same thing, very explosive. Before dynamite, nitroglycerin was the main explosive. And there's a problem because nitroglycerin explodes. You'd think that wouldn't be a problem, but the thing is that the nitroglycerin will explode pretty much no matter what you're doing. Like, you got nitroglycerin on the table here, and you like shake the table so it rotates back and forth a little bit, rocks, it goes kaboom. Right? You're trying to transport this nitroglycerin way up in the mountains, so you want to mine some rocks, and you don't want to sit there with a pickaxe because Minecraft is a terrible plan in this regard. What are you going to do? You're going to take some explosives, and you blow up a big hole. But if that cart shakes, it explodes. Well, roads up to the mountains aren't known for being perfectly smooth and flat the whole way with nice shock absorbers, especially not when you're back in the 1800s. So nitroglycerin was incredibly dangerous. Mining itself, always a dangerous profession. Anyone doing that, very dangerous. The ancient Romans used to get people to like slaves to do the mining because they didn't want to have to do it themselves. Mining is always a dangerous profession. Anyone who's a miner, props to them. Hard work. But we can make it easier. We don't need to give them explosives that blow up at the drop of a hat. That was the brilliant idea of a chap called Alfred Nobel. Now we're getting way off tangent, but this is a cool story. Alfred Nobel was the one who figured out how to make dynamite. Dynamite involves wood shavings, a bit of wood, other things like that, soaked in trinitrotoluene with a cap on the top made of gunpowder. So you'd have a fuse, you'd light the fuse would burn down slowly, hit the cap would then ignite the rest of the TNT. Much, much safer. It does not explode on its own, only explodes when the fuse hits it. You need fire. This made Nobel very rich, because he figured it out, he patented it, and if you wanted to buy some TNT, you had to buy it from him. How rich? Nobel. You heard of the Nobel Prize? That's his prize, with his money. What? Okay, let me explain. Nobel lived up in, I want to say Sweden, but I think it was actually Norway. At the time, I think it might have been Sweden and Norway were the same country, actually. Europe, a lot of wars. I'd have to check which one. He lived up there in the cold places. And the newspaper reported his death. He wasn't dead, but he opened up the newspaper Saturday morning and he took a look and he went, and the front page news said, "The merchant of death is dead." And he's like, "What?" And he read the newspaper. And the newspaper had a scathing article about how he was just the worst person ever because of all the dynamite and the explosives and all the pain and suffering that had caused. He was shocked. First of all, that someone would write this, and second of all, that this is what they would write. It turns out that someone else with the same basic name as him had passed away, and they assumed it was him, so they wrote their piece. He decided that he wanted to change his legacy. So he founded the Nobel Prize for those who advance human discoveries and bring peace to the world. The Nobel Peace Prize, the Nobel Prize for Science, and other things. He had no children, so he took his vast fortune and he put it towards the prize. How rich was Alfred Nobel? We're still using his money to hand out the prize, and we have handed out the prize every single year for the last 200-something years. It's a lot of money, all because of benzene. Okay, now to be fair, it's not like it's just a giant pile of money and we're just like taking some out with a shovel. It's invested in other things, and there's the Alfred Nobel Foundation, and finances is involved, which is basically magic, depending on how much you understand math. But the point is, benzene, aromatics, incredibly important. Also, that newspaper article changed the history of the world right there. With the discovery of that last attribute, oh yeah, right, the cancer, I forgot. Benzene and many of these things cause cancer. With the discovery of the cancer-causing properties of benzene, the material has become very tightly controlled. Originally, benzene, which people play with it, like probably we could have played with it in school. Turns out that was a bad idea because contact with benzene fumes and contact on your skin and other things will cause cancer. Because it turns out benzene reacts very easily with human tissue because we're organic and benzene is organic and it causes all sorts of trouble. Okay, back on topic, away from history. Let's go back on topic, Mr. C. Chocolate has aromatic hydrocarbons in it. We got the cocoa itself. These are aromatics. They're much more complicated. They're not totally benzene. This one here is benzene with some functional groups attached. We'll talk about those later. This one's a little bit more complicated. It's got some nitrogen in there as well, and it's got like two circles attached together. Like this one here is like an aromatic. This one's just a cyclo. Down here we can see another aromatic, right? This is another way to draw the aromatics with the little lines like this. So all of these chocolates rely on and get their flavor from aromatics. Similar, as mentioned at the top of the slide, coffee is filled with organic compounds. And you can see here, some of them are aromatics. We got aromatics with nitrogen in them on these two. We've got some aromatics with oxygen in them over here. We've got, this one is just a full-on benzene with some functional groups. There's that word again. Up here we've got, oh, there it is. We've got another one with some oxygen and things. So there are loads of, oh, this one here isn't quite an aromatic. See, it doesn't quite have the same sharing profile. It doesn't have all the double bonds. But again, these are key. Many of the different odors and flavors that we enjoy are aromatic based, along with many of the dyes that color our clothing or paint our walls or blow up the sides of mountains. Yay, Nobel. Okay, so how do we name these? Oh no, more naming rules. It's okay. It's okay. These are not as bad as the other ones. I mean, they're still bad, but they're not as bad. Naming rules for hydrocarbons with a benzene ring depend on if the benzene is the main chain or the branch. Basically, is benzene the main attraction with a side show sticking out, or is the side show, the long chain, the main attraction with a little benzene hanging off the end? That's what we're looking for, okay? So first one here. Case 1, benzene substituent. Benzene is a branch on an existing chain. That's our main one, so something like this. Okay, so there's a benzene there. Right, it's hanging off the middle, but there's a pretty big chain there. What is that? 1, 2, 3, 4, 5, 6, 7. That's 7. It's a heptane. Okay, so we got a heptane there with a benzene located in the middle. So that's option 1. Option 2, benzene backbone. Other branches are on the benzene ring. What does that look like? Like one of those, right? You got the benzene and then stuff is sticking off of it. Now, if we move back a little bit here to the coffee slide, right? Take a look at these ones, like this one here. It's not benzene, but the same idea. There are lots of things sticking off of the ring, the aromatic ring, the non-benzene aromatic ring. There's lots of stuff sticking off of this. So I'm going to talk about the core, the ring, and then mention these little branches. I compare that to, where is it? Maybe even this one over here. We've got a lot of stuff going on before we get to the ring at all. But even some of these aren't really a great idea. Didn't we have more with the coffee? Oh yeah, here, this one here. This one here, we've got a fairly long chain with a benzene ring kicking off the back, compared to this one where it's a lot of rings with some stuff sticking off. So that's what we're looking at here, okay? That's the definitions that we're working with. Aromatic rings still use all the rules for aliphatic chains, though there are some complications because it's a ring. Of course it gets more complicated. What else would we expect? The main problem is, where do you start counting? Because it's a ring, right? It just goes and goes and goes. Okay, we're going to look at benzene as a side chain first, because it's easier. So benzene is a branch on a longer parent chain. Benzene name is not used. Instead of benzene, we call it a phenyl. Why? History. Is it annoying? Yes. Does it matter? Not really. Here's the key. This one here, as we just said, it's 7. So there's heptane, and we've got ourselves a phenyl group, this thing, at what spot? Okay, 1, 2, 3, 4. So this is going to be 4-phenyl heptane. And there you go. Ta-da! That's it, right? It's the same rules that we already had, except now we've got another word. We had methyl, ethyl, propyl, and now phenyl. You treat it the same, just change the words at the prefix a little bit. Okay, so that one's easy. What do we do with this kind of thing, though? This one's a bit of a mess. This aliphatic chain ends in a benzene and has another side chain. If a side chain has a side chain, we use the original method. What do I mean? Rather than talk about this guy here and say that this long thing is attached to the benzene, I'm just going to say, you know what? This is the chain, and these two stick off of it. Okay? So this is 1, 2, 3, 4. Meth, eth, prop, bute. So it's butane. We've got, let's say count from here. 1, 2, 3. So this is going to be 1 phenyl, 3 methyl. We got to put it in alphabetical order. So the methyl first, then the phenyl. How would it look? There it is. 3 methyl hyphen 1 phenyl butane. Okay? So basically put, if the benzene is attached to a long chain, we go with the chain first. What counts as a long chain? Let's say anything bigger than 4. Right? In our list of substituents of side chains, we had methyl, ethyl, and propyl. If you get to butyl, if you get up to 4, just make it the parent chain. That's what I'm going to say. Okay? All right. Remember, always number your chain from the end closest to the substituent, right? So I don't start numbering over here. I start numbering over here because this is closest to the substituent. So this is going to be 2-phenylheptane, not, what did that be, 6-phenylheptane if I started from this side over here. So I don't start here. I start closest to the side chain, the closest to the interesting thing. All right. What happens when benzene is the main show? The main attraction is the benzene. This is case 2. This is the weird one. If an aliphatic chain terminates or ends at a benzene ring, and there are no side chains on the other side, or on the other side chains, we have a case kind of 2. Okay? So what do we do then? There are 3 options to a case 2. Oh no, there are options within our options. Option 1, monosubstituted. There's 1 side chain, something like that. Option 2, disubstituted. There are 2 side chains, something like that. Option 3, polysubstituted. You'd think the answer would be like tri-substituted, but no, we just go like 1 too many, which to be honest is how a lot of math works. Something like this. For all options, we use the suffix benzene, but the prefix changes. Okay, so for all of these, it's going to be benzene, benzene, benzene at the end. But the beginning will be different. All right? Let's take a look. The mono one is the easiest because we just use the prefix for the substituent and toss benzene at the end, right? So this one here is 1-methylbenzene. This is 1-ethylbenzene. This is 1-chlorobenzene, right? Very simple. There is a single whatever. It is located at the first spot. Why is this the first spot? Because that's where something interesting is. So we start counting there. We could have started counting here. Right? I could call this 1, 2, 3, 4, 5, 6. But why bother when I can just make that 1? So I'm just going to make it 1. Okay? That one's easy. What about di? For two substituents, things become tricky because aromatic is a ring, so there isn't really a start or end. So use the smallest substituent as the start line and name the others based on their relative location. Okay, let's take an example here. So here we go. 1,2-dichlorobenzene. Right? Position 1, position 2. Or I could say position 1, position 2. They're both identical. That one's pretty easy. Okay, here's another one. Okay, so we start counting from one of them, like maybe this one here. This is 1, this is 2. So this would be 1,2-dimethylbenzene. Right? There it is. So I think you can see that these are all pretty straightforward, really. Like, we've just changed the ending, but otherwise the rules are pretty much the same. With the key rule, as I said there, start counting from the smallest substituent, and you sort of count towards the other ones, right? So like I could start here and go this way. Don't do that. Start here and go closest. Shortest route, shortest route. Be lazy, guys. Be chemists. Okay. Chemists also decided to develop a totally different method for naming disubstituted because, of course they did, things weren't difficult enough. Use the smallest substituent as the start line and name the other substituent based on the relative location. Basically, they decided numbers were too much work. They want to do something other than numbers. What did they do? This. What? Okay. So there's my start position because it's the smallest one. If it was be next to the start position, then we'd say that the next one was ortho. If it was opposite, we'd say para. And if it was one removed, we'd say meta. That's what meta means, one removed. The meta-analysis. My analysis is one removed from the basic. There it is. Ortho side by side, meta one step removed, and para is opposite. Okay, let's take a look at this in action because we're going to need some examples. So here's some examples. Ortho-dichlorobenzene, meta-dichlorobenzene, para-dichlorobenzene. So the only thing we've done here is we've removed the numbers. So instead of saying 1,2-dichlorobenzene, we just say ortho-dichlorobenzene, and it tells the person they're next to each other. I don't care where we put them on the ring, they're next to each other. That's the key thing. Now, the advantage of this is that you don't get hung up on counting the numbers properly. It's just they're next to each other, we're done. I don't care. This, they're one step removed from each other. Here, they're opposite each other. So the advantage is it's less ambiguous. The disadvantage, it's more work because it's a totally new system. You'll notice, though, that underneath, I've got the new method. I've also got the old method. They're both right. And if you just stick with this one, I'm fine with that. You don't have to worry about going into this ortho-meta-para stuff. It's there. It's useful. It is less ambiguous because you don't have to worry about somebody counting wrong. Ortho means next to. Meta means one removed. Para means opposite. It's less ambiguous. That's the only reason this exists as a system and because they wanted to use more Greek words in their things. Okay? So here's some other examples. They're all the same thing. These are all named in different ways. Again, with the laziness coming out. Ortho-dimethylbenzene or O-dimethylbenzene or 1,2-dimethylbenzene. See, this is why it all came around. Oh, it's one letter. I don't have to write all the words. There's so much less work. Yeah, no, not really. But when you have to do this a billion times, yeah, maybe. Okay. Now, going for our last one. Oh, no, that was only the second one. There's a third option, polysubstituted. What crazy method do they have? No, they don't have any. We go back to the numbers again. It's only for the di method that they have their whole new system because why not? So we drop the ortho meta pair, we go back with the numbers because it's easier. Use the smallest substituent as the start line and name the other substituents based on their relative location. Just like before, this would be 1,2,3-trimethylbenzene. Why is the 2,1 special? Because they wanted it to be. They didn't need to. They could have just kept the same method the entire time. I know. Anyway, next topic. Organic functional groups. Take a look through your book, guys. There's a ton of practice on this stuff. Don't forget the answer key is located online. Next time, we're going to be taking a look at organic functional groups, and we're going to understand what all of this stuff is. We've mentioned this a little bit, but that will be next time. And I will see you guys then.